good day to all, and thank you for joining us from all around the world. Hello, I am Lucinda Offer, Executive Director of the Mars Society, and I am proud to be opening our 23rd Annual International Convention virtually for the first time in the history of our organization. Thank you to the people and organizations that allowed this to take place, namely our IT Director, James Burke, Attendify, and Zoom. This online event is allowing us to reach further than we've ever reached before for a larger engagement and a worldwide interest in humans to Mars. We thank you for making this possible. One thing I have learned this year, and all that I have been privileged to be involved in, with either my role as Executive Director with the Mars Society or my day job at the Royal Astronomical Society in London, formerly as a NASA Ames Associate conducting Mars analog research, as a volunteer with our new International Education and Outreach team, or in fighting this pandemic. What we do in this world is not accomplished by any one individual alone. It takes a team and teamwork, and we must work together for all of us. Along with our convention theme this year of Rising Together to Mars, we acknowledge that a Humans to Mars mission is an international effort, and that was apparent this year with multinational missions to Mars. It is an interesting time, and it is a humbling time, for we have learned how vulnerable we are and what we can accomplish when we work together, while practicing inclusivity and being open to new innovative ideas from partners around the world. And I think if we can continue that forward, we can have humans on Mars in a decade. We thank you for being here with us and rising together to Mars. Welcome. Before we get to our speakers for today, we have just a few reminders. Remember, when joining a talk, please set your camera and audio to off. Another helpful reminder, if you are a speaker with us today, turn off your notifications on your devices for the time being. There is a Q&A box for you to post your questions for the speaker. And please remember, our convention this year is free, but we are asking for a donation of $50 or whatever you can afford to help support our nonprofit organization. We didn't stop because of COVID, but many of our typical funding sources did. So we've added a donation button in the navigation panel on Attendify. Please look for the $ icon. Every little bit helps, and thank you in advance. Also, please consider joining the Mars Society as a paid member. Membership gives you several benefits, including discounts in our online store and for future events. We have added additional merchandise for the convention, including t-shirts, sweatshirts, our official convention poster designed by Samer El-Sayeri, and other items. Click on Exhibitors in Attendify to find the link, or go to store.marssociety.org. We have networking tools via Slack and Wonder. Those links can also be found on the left-hand side navigation bar in Attendify under Convention Info. On Slack, we have the Help Desk channel, or you can ask using the Q&A feature in this Zoom call. Okay, let's get on to Mars. Our first speaker started out as a science teacher when the possibility of humans reaching Mars inspired him to begin a career in engineering. Decades and hundreds of technical and non-technical publications later, including the book, The Case for Mars, The Plan to Settle the Red Planet and Why We Must. Please welcome who I consider the most important influencer of the 21st century, our president of the Mars Society, Dr. Robert Zubrinem.
Hello, and thank you, Lucinda, for that very generous introduction, and thanks all of you for coming. This is going to be a fantastic event. We now have 5,400 people registered. There's 150 speakers, and including the NASA administrator, and another one that I'm going to announce very shortly. But we are gathered here now at a time of unique opportunity, a juncture in time to set humanity's course towards Mars. Now, it is said that politics is the art of the possible. Well, engineering is the art of making the impossible possible, okay? And in other words, engineering is upstream of politics. We make it possible, and then they do it, okay? And there's no better example of a person who has shown that it is possible to make the impossible possible than Elon Musk. And so it is my great pleasure to announce to all of you that Elon Musk will be addressing the conference at 4 o'clock tomorrow. So get the word out on that, put that on your agenda. The talks that are there now will be moved back to make room for it. They'll be given shortly after he talks. But what Musk and his team have shown, that it is possible for a well-led entrepreneurial team to do things that had previously been thought necessary to take 10 times the cost, 3 times the time, and even deemed impossible to be done at all, such as reusable launch vehicles returning to their launch sites. And as a result, he has set off a wave of creative activity of other people getting into that game and related games. We're having private investment funding SpaceX's for spacecraft and space instruments and all sorts of things. And collectively, this is going to make it all possible. And we'll be hearing a lot more about the SpaceX effort from Elon himself tomorrow. So I won't go into it, but suffice to say that from where we stand now, it looks like that relatively shortly in time, and whether it's this year, next year, the year after, within a very few years, there's going to be reusable heavy lift boosters with the capability of the Saturn V, but 1% the cost. And that is going to make a lot of things possible, including most notably humans to Mars. Okay, now where'd that come from? Okay, well, Musk was recruited by an idea. Okay, the idea that it is necessary to make humanity a spacefaring species, multi-planet civilization. A lot of his team, okay, and they work twice as hard as people at most aerospace companies and actually get paid less, but they do it because they believe in the idea, and that's why they make it happen. And these other people, and Victor Hugo said, nothing can stop an idea whose time has come. And that is true. If the idea has messengers that can recruit to its banners the forces required for it to prevail. And that's what we need to do. So we need to take advantage of this opportunity, now that this is becoming possible, to make Mars humanity's, put it on the agenda for this decade. Okay. Now, why should the goal be Mars? Okay. I would give you 4 reasons: for the science, for the challenge, for the future, and for our survival. I'm going to talk a little bit about each of these. First of all, for the science. Okay. Now, Mars is the Rosetta Stone for letting us know the truth about the potential prevalence and diversity of life in the universe. But that itself is only the entrance to the area of science. See, what is science? Science is mastery of the laws of a phenomenon, okay? To actually understand the laws governing a phenomenon. And this has many engineering implications. From the mid-1700s through the late 1800s, people mastered the laws of electricity and magnetism, and thus were able to introduce entire realms of technology that had been completely unexpected and unimagined before that. Starting with telegraphs and motors and going on to radio and television and now internets and all of this. And so it opens up new worlds. Now, in the 19th century, we mastered basically the laws of electromagnetism and chemistry, okay? And this created the world of the 20th century. But there's another science which is going to become increasingly important. I believe it's going to be the revolutionary science of the 21st century, and that is biology. And we only discovered the alphabet of biology 60 years ago, Watson and Crick, DNA, okay? We're still just basically learning our DNAs, our ABCs of biology. We don't know, we're beginning to learn to read it, but all life on Earth uses this one alphabet. It uses this one language. Is this true for life in the universe? Okay, it's one thing to be able to read, it's another thing to be literate. And, you know, if we go to Mars, we could find out if what we think is the language of life, or it's just one example of a much vaster set of possibilities for the language of life, the system of information for carrying from one generation to the next. Okay, you know, we're going to discover what life is. And of course, we are life. We're going to discover what we are, okay, by going to Mars. And this is enlightenment, and the technological ramifications of this will be phenomenal, okay, as phenomenal as discovering the laws of electromagnetism, okay? Because what life is self-replicating nanomachines. We're just beginning to read it. What happens when we learn to program it, okay? What when we actually understand it? Then there's the challenge. I believe humans are like societies, are like individuals. We grow when we challenge ourselves, we stagnate when we do not. A Humans to Mars effort would be an inspiration, a challenge to every young person. Learn your science, and you could be part of this grand effort to explore and pioneer new worlds. And out of that, we would get millions of young engineers, scientists, inventors, technological entrepreneurs, doctors, medical researchers, just as we did from Apollo in the 60s when we doubled our science graduates. This would be global. It would include both men and women. It would be a tremendous impetus for human progress through the creation of capital. Okay. And then there is the future, okay, which is, okay, very simply, is that this is a beginning. If we do what we can do in our time, which is establish those first towns on Mars, those first exploration missions, bases, settlements, the seeds of new branches of human civilization around the world, we will open the door to humanity's career as a multi-planetary and ultimately interstellar civilization, such that 500 years from now, there will not only be new nations on Mars with new languages and cultures and everything that goes with it, but on thousands of planets orbiting stars in this realm, a region of the galaxy. And, you know, they will have technologies that are unimagined. They will be multiple centers for creation of new science and technology. They will have new literatures. They will have new histories of great deeds that will be used to inspire people to do even grander things. And you know, that is something grand and wonderful that we can create. And when you have it in your power to create something grand and wonderful, then you should. And then finally, there is for our survival. And what do I mean by this? Do I mean, well, we should become spacefaring and go to Mars so that if the Earth is hit by an asteroid, there'll be some survivors elsewhere? That might be said to be one benefit, but that does not impress me at all. Even now, it's true, if we become spacefaring, we will have the capacity to redirect asteroids so they do not hit the Earth. So as far as that is concerned, I mean, we're not going to space to desert the Earth. We're going to space to protect the Earth. Okay, but it's more vital than that, because the chance of an asteroid impact in the 21st century is low. But there's a much more immediate threat to humanity. Okay, people talk about existential threats to humanity. They talk about climate change, resource exhaustion, possibility of global pandemics, and all these are issues to be contended with. But none of these were the cause of the great disasters of the 20th century. The great disasters of the 20th century weren't caused by natural disasters or resource exhaustion or climate change or anything of the sort. They were caused by something entirely different, which was bad ideas. And in particular, one bad idea. And what that bad idea was, which came in a number of forms, is that there isn't enough to go around. There's only so much here, and sooner or later we're going to have to fight over what it is and what is there. And if you have that mindset, well then for one side or the other, sooner is going to be more advantageous than later. So 1914, German general staff looked at the crisis and said, we're going to have to fight Russia sooner or later for control of Eurasia. Should it be sooner or later? They said, let's do it sooner before they industrialize. Same thing in 1939. And same thing with Japan's attempt to destroy China while it was weak. And today you have this emerging confrontation between the West and China, or apparent so, and I happen to know, because I have talked to them, that there are people in Washington, D.C. who believe that war with conflict with China is inevitable because there's only so much oil in the world, and if they all have cars, there isn't going to be enough for us. And you can bet that there are people in Beijing who are thinking exactly the same thing from the other side of the chessboard. And if this kind of thinking is allowed to prevail, we will destroy ourselves. Okay, but it's not true. It is not true that the human condition is one of disparate nations in a struggle for survival over limited resources. Rather, what is true is that we are a family of nations, rather disorderly families, to be sure, but a family which are each making different kinds of contributions to things that expand the human prospect. Okay, China is progressing rapidly right now because the technologies invented in the West. But the West's own technological revolution owes itself to technologies invented in China, like paper and printing and so forth. And inventions made everywhere ultimately contribute to and are used by people everywhere. Okay, so that is the truth. But people don't see it. It seems intuitively clear, falsely, but intuitively, that there is only so much, and so we do have to fight. But if we can show, if we can make it tangible, if we can make it sensuous, that there isn't a limit, that by working together, even if it's in a competitive way, as it probably will be, okay, but nevertheless, all working on a common project to open up a new planet, and it becomes clear that it is silly to be fighting over provinces, okay? And that it's not true that there's only so much to go around on Earth, because the Earth comes with an infinite sky, and it's possible to throw it wide open, okay? So let's make the impossible possible. That's what we need to do. And I'd be delighted to take questions. Are there questions, Jim?
Dr. Zubrinem?
Yes.
How do you aim to combat the biological implications of the absence of a magnetosphere on Mars? Okay,
look, on Earth, we are not shielded from space radiation by the magnetosphere substantially. We are shielded by the atmosphere. The atmosphere that's above you, if you're at sea level, is equal to 10 meters of water sitting on top of you. That's massive shielding. The magnetosphere does provide some shielding against solar flares to people in Earth orbit. It does not shield against cosmic rays substantially, which is why the cosmic ray dose at the space station is about half of what you get in interplanetary space, and about the same as what you would get on Mars, because the Earth beneath you blocks out half the sky, as Mars would if you were on it. In terms of Mars expeditions, the radiation dose is actually a minor portion of overall mission risk. In terms of Mars settlements, where you are raising children, you probably would want to adopt systems of architecture that shield out most of the radiation most of the time, so that most of the habitat could be underground. They could, you'd have domes above them, but whole systems analogous to subway systems on Earth of habitation below. And so there would be only modest radiation dose when you went to the surface to run your greenhouses or to explore.
Next question. What are your thoughts on the Superhook transportation system?
Well, I'm not familiar with anything of that name. I have heard of transportation systems called skyhooks or space elevators. Now, with current materials, space elevators are not possible on Earth. The mass of the tether to make it strong enough to lift a load of any size off the surface of the Earth would be trillions of times more than the mass of the payload. But this is because there's an exponential function of the strength of the tether to lift the actual load has to be a certain amount and therefore a certain thickness, and then the bit of tether above it has to lift both the payload and that bit of tether, and so on. Now on Mars, the gravity is only 1/3 Earth, and it turns out that you could use a skyhook on Mars. I would hang it from Phobos down, so it would travel over the equator, and it would have a velocity relative to the surface of Mars of about 600 meters a second, I think, as I recall. And what that means is that a rocket taking off from the surface of Mars could rendezvous with that on a suborbital trajectory and catch it, okay? And then ride it all the way up to orbit in Phobos or beyond Phobos. If there was a tether pointing outward, it could be sent back to Earth or out to the asteroid belt or anywhere you want to go. The advantage of this system, once you install it, is that taking off of Mars to, say, return to Earth, instead of requiring a 6 kilometer a second delta V, would only require a 0.6 kilometer a second, 1/10 as much propulsion. And so that would be a very useful piece of infrastructure to put in place once Mars settlements are there to take advantage of it.
All right, thank you. Once the prohibitive bottleneck in transportation is resolved, what do you think is the next biggest challenge in establishing a permanent human settlement?
Well, okay, that's an excellent question. Okay, look, the SpaceX people are working on resolving the transportation system, which is the largest single piece of development that needs to be done to enable humans to Mars. But there's a whole bunch of other technologies that are needed. There are Mars spacesuits. There are surface power systems, and it'd be very advantageous, for example, to have nuclear power systems on the surface of Mars because the solar energy there is only 40% as strong as Earth, and it's unreliable, can be shut out for months by dust storms. So we need space nuclear power. And this would be very difficult for a private enterprise company to develop because the materials are controlled. And then there's in situ resource utilization systems to make rocket fuel and oxygen on Mars, and automated greenhouse systems, and also surface mobility systems. And many of these things do not have as clear a commercial applicability as a space transportation system does, and therefore are also harder to develop in the private sector. And so I think what we're going to need to make this happen is a public-private partnership. But I think that by developing the transportation system, by basically holding out his hand to NASA and saying, meet me halfway, we'll be able to get them to meet halfway. I mean, starships will certainly be flying to orbit, in my view, by 2024. And, you know, someone's going to be elected president in 2024. And, you know, Winston Churchill once said that the American people can always be trusted on to do the right thing after they have exhausted all the alternatives. And, okay, so now we're trying a new alternative, and if that works out, fine. And if not, we'll try again in 2024. But look, if starships are flying to orbit in 2024, whoever's elected then will turn to his or her advisors and say, look at this. can we have people on Mars by the end of my second term? And the answer is going to be yes. And will it cost hundreds of billions of dollars? No, it can probably be done within the existing NASA budget. Well, then let's meet them halfway. Let's develop this other stuff. Let's make this happen. I want this done by 2030, and it will be possible to be done by 2030. And so we're going to have our job cut out for us to make it clear to the political class that the possible is now possible. But once that becomes clear, we can make it happen.
All right. This is a two-part question. What is the most important thing that individuals can do? And another question closely related is, what is the best way to reach our political representatives?
Well, look, there's all sorts of things that people can do. Okay, if you're a technical person, you can participate directly in the effort. You can enlist under the banner of SpaceX or Blue Origin or Lockheed Martin or NASA and lend your talents there, or you can join with others in starting your own entrepreneurial effort focused on meeting a key unmet need that to, once again, put another piece of the puzzle in place. Okay, so you can do that. Now, if you don't have technical or business ability so that you can't participate directly, you can help spread the word. As I said, engineering is upstream of politics, but the thing that's even upstream of science and engineering is aspiration. And this is why, the British poet Shelley said, poets are the legislators of mankind. They establish the vision, so you can write. Or if you're not good at writing, just spread the word in any way you can, okay? Help recruit more people to this effort, whether they are technical people or political people or anyone of this kind. So Mars needs engineers, Mars needs scientists, Mars needs businessmen, and Mars needs poets.
Next question. What is your position on using the moon as a means of reaching Mars ultimately?
I don't think that's a good plan. The delta V required to go from low Earth orbit to the surface of the moon is greater than that to go from low Earth orbit to the surface of Mars. So even if there was rocket propellant sitting on the surface of the moon today available for free to anyone that would drop by, it would not make sense to go there and get it. Now, if they launched it to lunar orbit and had it available there for you, then the delta V to go there and get it would be the same as going to Mars. So once again, not particularly useful. Now, this is not to say that we shouldn't go to the moon, but people advocating going to the moon should not say, and it is not useful for them to say to people wanting to go to Mars, you can't do your program until you do my program. Okay, that is not true, and it is not useful. If we develop the capabilities that allow us to go to Mars, they will also allow us to go to the moon. If we and there are some things to be done on the moon, but they are no means as profound as going to Mars. Now, I have to say that despite that, I have a mixed view on the NASA Artemis program because I do think it is the wrong objective, but at least it is an objective. And by saying that the NASA Human Spaceflight Program is committed to accomplish something within a specified period of time, what the Bridenstine and the Pence have done is they have injected a lot of energy into NASA, into starting to think about actually accomplishing projects. And if we did go to the moon before we went to Mars, that would certainly do a lot to restore NASA's can-do spirit. And there's a lot to be said for that in that respect. So we could go to the moon before we go to Mars. We could go to the moon after we go to Mars. We should go to both the moon and Mars. But it is simply, from an engineering point of view, not true that we need a lunar base or a lunar orbiting space station or a Mars orbiting space station to go to Mars. If you want to go to Mars, you figure out how to do that and not how to use the Mars mission as an excuse to justify a variety of other projects that don't necessarily contribute. So I think we'll have a base on the moon. I think there's some things we can find out. I'd love to put some telescopes on the surface of the moon. But overall, in terms of how we make humanity into a spacefaring civilization, and in terms of how we inspire the next generation to want to do great deeds, you're not going to do it with something to attempt to repeat what was done by their grandparents' generation. And once again, to establish a new branch of human civilization, we have to go to a place where there's the large majority of materials needed to create the resources for a civilization. And that is Mars.
Thank you. This question is from a high school student. What advice would you give her generation as far as preparing themselves to go to Mars?
Well, if you actually want to go to Mars, if you want to be in the first wave, you want to be a scientist or an engineer. So learn all the science and math and, that you can, or perhaps a biologist, perhaps a doctor. Okay, those are the professions that will be in the first wave that go to Mars. But ultimately, as Mars develops as a society, we'll need more than scientists and engineers and mechanics and agronomists. Okay, we're going to need teachers and playwrights and community orchestra directors. So we're going to need people of every skill and every talent. So this is a project for humanity, and everyone can participate, either here on Earth or in some cases by going to Mars themselves. So I think I'm out of time, and thank you very much. I look forward to the rest of the conference.
Thank you, Dr. Zubrinem. Thank you for your time and kicking us off with our first speaker. We're going to move on to our next. And I wanted to say I had the honor of working with him at NASA Ames, as he is my former supervisor. And I had the privilege of being a part of a very inspirational NASA spaceward-bound team attending analog expeditions around the world. He is another monumental figure in the Humans to Mars arena, as well as a respected senior planetary scientist and astrobiologist at NASA, whose research focuses on the evolution of the solar system and the origin of life. Please welcome Dr. Chris McKay.
Hello, Chris McKay here. I'm going to start my video and share my screen. I'm going to use slides, so give me a second here to get organized. You should be able to see my slides. Jim, can you confirm that that's the case? What I'm going to talk about is good. I'm going to talk about what I call the prerequisites to human activity on Mars. And I've got my email there and the date. And here's what I mean by Mars. We think about, when we talk about Mars, the case for Mars, we can parse it into four steps. First step, short-term missions involving a few astronauts. Second step, long-term research outposts, tens, maybe hundreds of people, similar to research outposts in the Antarctic. Antarctic research bases are a good model. Next step would be large settlements with populations in the thousands or even more. And finally, a vision of terraforming Mars to make it easily habitable for humans. So that's what I call the story, the Mars story. What I want to address here is the question, are there fundamental uncertainties in our ability to really implement these steps. Obviously, there's engineering challenges and projects and funding and things like that, but those are solvable issues. They may be difficult, but they're solvable. I want to talk about fundamental issues that may be much more difficult. The first one is the question of, is there life on Mars? The second one, is Martian life a second Genesis? The third fundamental question is, how will life adapt to 1/3 gravity? And then the fourth fundamental question is there enough nitrogen, CO2, and water on Mars for terraforming? Each of these questions comes up in one step: humans, bases, cities, planets. And I'll go through each of them one by one and discuss the points. Here is the first question: is there life on Mars? Now we're imagining, as you see in this picture, sending humans to the surface of Mars in the equatorial areas. The general view is that the low latitude surface of Mars does not have life. It is lifeless. That's the scientific interpretation of the Viking results. But the evidence is scant. There's only been one mission really that's focused on life detection. And the evidence in hand probably does not constitute due diligence with respect to returning Martian materials to Earth, e.g. the astronauts coming back, dust on their suits, dust in their lungs, dust on their hair. We are required by the Outer Space Treaty to be very careful in returning materials to the Earth for obvious reasons. So I think what this means is that we have to do a better job purely for this requirement, if for no other reason, to search to confirm that the surface of Mars has no life. So what we need, I think, is an in situ no life detection mission in advance of humans, so that we can check the box that, to the best of our ability to determine, the equatorial regions of Mars where humans would go and return from meets the Outer Space Treaty requirements for not contaminating the Earth. No life. So we need a no life detection mission. The next question, if there is life, is it a second Genesis? And I bet this question will not come up until humans are on Mars, because if there's life on Mars, it seems to be in very restricted locations deep below the surface that will probably only be discovered by human exploration and deep drilling. And in fact, this is one of the main motivations scientifically for human exploration, is that humans and the infrastructure they have can do this sort of extensive exploration. So if we go to Mars, the surface is lifeless, but the deep surface has life. And if that life represents a second Genesis, then this has implications for human presence. And I think the solution here is we must do our exploration in a way that's biologically reversible to keep the options open for what we decide to do if we find life that is a second Genesis. The next fundamental question is, can life adapt to 1/3 gravity? Near-term missions, even the Antarctic-like bases, may involve humans going back and forth to Mars. They probably do not involve families with little kids and pregnancies. Antarctic bases aren't known for that. But if we're talking about cities on Mars, we have to think about what that's like. And how will life, reproduction, growth, early development, and 1/3 gravity be? Essentially, we're assuming that life will adapt well. As we conceive of cities on Mars, we're assuming life will adapt well to 1/3 gravity. But there is no data to support this assumption. And I say no data, I mean zero data. We haven't even done simulations in Earth orbit at 1/3 G with anything farther up the phylogenetic tree than a plant. So we have no data on how humans will adapt, how pregnancy will be carried to term, how infants will be born, how children will develop at 1/3 G. Now, if long-term growth and reproduction in Martian gravity is determined to be detrimental, this has important implications for the long-term human presence. We can certainly still go there, short visits, and maybe even large permanent research bases. But the idea of large cities with thousands and more people becomes harder to imagine. Finally, in the fourth phase, terraforming, the key question, surprisingly, is not can we do it, because we clearly can if the materials are there. We have learned to our surprise that we humans can warm up planets. And when I mean surprise, here on Earth, we've been surprised. And we could do the same thing on Mars. On human timescales, we could warm Mars with super greenhouse gases. But it's pointless to warm Mars if there's not enough material on Mars to make a biosphere. And that material is nitrate, CO2, and ice. How much nitrate is on Mars? We don't really know. We know it's there, but we don't know how much is there. How much CO2 is present as ice, carbonate, or minerals? We don't know. People have written papers suggesting it's this or that, but we won't know until we do deep drilling and do geophysical surveys. The question of volatiles on Mars is fundamental. If there's not enough of this material, then terraforming becomes science fiction. It moves to Star Trek-like technology and epics, and that may be still interesting, but it's not part of a near-term plan. So I want to go quickly to questions. So on the way to Mars, as I've said, and people have pointed out, there are many practical difficulties with human activities on Mars. We've got to develop biological life support systems, power systems, spacesuits, artificial gravity, dust control. These are hard problems, very hard problems. Some of them we don't even see clearly how to solve, but they're all solvable in principle. With effort and focus, we can solve them. And they are solvable here on Earth. We can solve them before we go to Mars. But the questions I've raised, the questions of life, second genesis, adaptation to 1/3 gravity, and inventories of nitrogen, CO2, and water are fundamental. They're actually not questions or problems to be solved. They are issues that can only be answered. The answers to these issues can only be discovered on Mars. Mars will tell us if there's life, if it's a second genesis, if we can adapt to 1/3 gravity, and if there's enough nitrogen, CO2, and water. We have to discover the answers to these questions on Mars. It cannot be answered on Earth. And unfavorable answers to these questions could derail the Mars story. Now, what's the point of this is that we ought to focus on some of these questions in terms of the robotic missions that go before humans and the initial science and field activities that humans do when they are on Mars. And as a good academic, of course, I write all this in papers and publish them in peer-reviewed journals. That's what scientists do. So here, for your entertainment, is a list of lots of papers which go over these thoughts in detail, much more detail, obviously, than I can cover in a half-hour talk. And I'll happily send reprints, PDFs of these to anyone who wishes to have them. And this is the last slide. And Jim, I'm going to disconnect my sharing and open up for questions.
Hi, Chris, this is Lucinda. We're going to have Nora Hovey help us with the Q&A. So
Okay.
Nora, whenever you're ready.
All right. This is from Jerry Stone. What is the view of Gil Levin's experiments on the Viking landers? The positive results were overruled as the mass spectrometer found no carbon, but that was later shown to be faulty. So is it possible that we did find evidence of life on Mars back in the summer of 1976?
Yeah, that's a very good question. And it's one of the reasons why I contend that the question of life is not closed. Although most Mars scientists do not agree with Gil that he detected life, I don't think we can rule it out to the level of certainty that would be required to bring a sample back to Earth. So there's one level of certainty, which is the consensus in the scientific community. Okay, the consensus in the scientific community is Viking did not find life. What Gil detected was chemical reactivity. But is that level of certainty adequate to risk Earth's biosphere in returning a sample from Mars? I think clearly the answer is no. It would not stand up in court against a challenge that we had not achieved due diligence with respect to our obligations in the Outer Space Treaty. So this is an important point. The question of life is not locked down well enough to allow a human return. We need to do a no life detection mission. And hey, Gil might have been right. And this mission we send to Mars to confirm there's no life there might surprise us all, and Gil would be having the last laugh. I actually hope that's the case. I would love there to be life on Mars. But the expectation is it wouldn't be there, and what we have to do is document that well enough that we meet the standard of proof for the Outer Space Treaty and our legal requirements to protect the Earth.
Next question. Can you comment on any projects in the works that would scan for deeper water so we might know where to drill?
Yeah, that's a good question. When you say scan, then you could imagine radar. And in fact, there was a paper in Nature's scientific journal just a couple weeks ago, reporting on radar evidence for deep lakes in the polar regions of Mars. So indeed, we can scan the subsurface with radar, and we can look for subsurface lakes. And to everyone's surprise, we seem to have found some below the ice in the polar regions. Maybe we'll find some below ground in the equatorial regions. But we don't really get very good information from just these radar. We're really going to need to drill. The way we find out what's underground is to drill. So I would rephrase your question, if I could, as scan and drill for subsurface water or other resources. And drilling is very hard to do with the robots. Curiosity got a few centimeters. ExoMars in a few years will get 2 meters. That just doesn't do it. We need to be able to drill a kilometer. And for that, humans are particularly well equipped. The best way to drill a kilometer is send a drill rig with a bunch of roughnecks, and they'll drill down a kilometer. So I've always contended that drilling deep below the subsurface is one of the most important scientific tasks that humans can do when they get to Mars. So if you want to be on the first crew, learn how to drill.
Next question. Can you explain the second Genesis theory?
Thank you for that question. It gives me a chance to go into one of my favorite topics in more detail. The interesting thing about life on other worlds is not just that there's life there, but that life might be fundamentally different from life on Earth. It might represent a second origin of life, what I call a second Genesis. Now, for many years, it was just assumed that if there was life on Mars, it would be a second Genesis. Aliens were from other planets. And if you were from another planet, you were an alien. But now we know that Earth and Mars exchange material via meteorites. And it could be that life started on Mars and was carried to Earth in meteorites, or vice versa. So we might well go to Mars, find life, and find that it maps on our tree of life. Google tree of life to see what I mean. And if that's the case, then life on Mars and life on Earth are related. There are cousins. Well, we might as well just move right in. Hi, cousins, here we are. If we go to Mars and find that there's life there and it is fundamentally different than life on Earth and represents a second Genesis, that's amazing, because it would tell us right away that n equals 2. N being the number of life forms in the universe. It's at least 2. Right now, we only know that it's 1. If we find a second Genesis on Mars, it would tell us that n is greater than or equal to 2. And by the by the 0, 1 infinity rule, 2 doesn't make any sense. You go from 1 to infinity, really. So it would tell us the universe is just full of life. Wonderful. But it would also pose the fundamental ethical and technical issue of, if there's life on Mars already, how do we establish life there, or do we establish life there? So it becomes much more problematic in terms of the story that I talked about at the beginning, if we find a second Genesis of life on Mars. It's also, but it's much more scientifically and philosophically interesting. but it poses very important ethical and practical problems of contamination and infection and who knows what. A good cautionary tale in this regard is rabbits in Australia.
Next question. This one is gives you an opportunity to dream a little. Once a permanent human presence has been established on Mars, what's the next step?
Well, I see 4 steps again. Small missions with a few astronauts, permanent long-term research bases, large cities, and then terraforming Mars. So those are the steps. Beyond that, okay, we've done that. Let's say we've gone to Mars. Everything's been fine. All of our questions have been resolved positively. We have cities on Mars. It's terraformed. Where do we go next? I think that's a really interesting question. I have no answer to it. There's nowhere else in our solar system that's anywhere near as good. The nearest stars are very, very far. I am afraid we might just end up sitting on our thumbs on 2 planets for a while.
Robert, do you have a question?
Okay, I have a question for Chris. Why do you imagine that the Outer Space Treaty is a problem that we cannot solve?
Well, the Outer Space Treaty, the US signed the Outer Space Treaty, and one provision of it is that we have to, quote, prevent the harmful contamination of the Earth. Now, we are bound legally, unless we step aside from the treaty, but logically, I think we have to have a very high precautionary approach to bringing back material from Earth that might have life in it. That is encoded in the Outer Space Treaty, but it's also part of the mandate of agencies like the Department of Agriculture. You want to bring something into the United States from the moon or from space, it's got to be cleared by the Department of Agriculture, and they care about, is this a possible contaminant? So. Yeah. And common sense tells us that we don't want to bring back life from another world without understanding it.
Okay. Well, those are arguable propositions, but they do not fall into the same category as humans cannot adapt to 1/3 gravity. Treaties, there are innumerable treaties that have existed in the past that have been abandoned or modified.
That could be the case. I'm not sure that I would advocate that we abandon the approach of not bringing back, or being very careful, extremely careful, and bringing back samples to Earth from anywhere that might contain alien life. Right now, that list on my part would include Mars, and it would include Enceladus. Sample return from Mars or Enceladus should be, even if you abandon the space treaty, should be, by common sense, treated with extreme carefulness and caution. And so astronauts coming back, it'll be very difficult to contain dust and Martian material if they're coming back, if astronauts are coming back. So it's much more efficient to get that question out of the way before astronauts come back. If you look at the way they did it on Apollo, they tried to do the containment and control with the astronauts' mission, and it really didn't make any sense. It was a farce. Well, fine, the moon, no one really had any serious concerns about life on the moon. But on Mars, I think the level of concern is going to be more severe. And so just from an engineering efficiency point of view, if you can check that box and discard it before you bring the astronauts back, you can dispense with any sort of control or issue of, are the astronauts bringing back dirt? Do we have to quarantine the whole capsule? And you could do that with a, quote, no life detection mission. Those missions are, I think, on the outside, even if NASA launches it, maybe $500 million. That will be probably a fraction of the cost of dealing with quarantine on the astronauts if you don't do that in advance.
Well, you can never prove a negative. And So a mission that goes to one place and doesn't detect life would not prove that there's no life on Mars.
Correct.
And if
Correct.
there is life on Mars, there's very little reason to believe that it would be pathogenic to Earth. But nevertheless, while we can debate that, and we have debated it, and certainly the scientific community does not believe that it should not do a Mars sample return until it is proven that there's no life on Mars. So I find myself in an unusual position of arguing the orthodoxy. But nevertheless, the fact is that while one can debate whether one should or should not do this or that, it is not beyond human power to deal with that situation. If Mars was a lush planet filled with life, that would not rule out going there unless we choose to rule out going there. It is not in the same category as there is not enough material on Mars to terraform the planet. Treaties can be changed by people deciding to change treaties.
Well, this is not really about a treaty. This is about risking the Earth's biosphere. Would we bring back a sample? Now, you say that the science community thinks that they'll bring back a sample without worrying about that. I'm not sure that's correct, and that hasn't been approved, by the way.
Well,
So,
no, the science community, though, is saying that it's willing to bring back a sample before it proves that there's no life on Mars.
But
Okay, because actually you can't prove that there's no life on
no,
Mars.
we're not. If you noticed, I'm not saying we have to prove that there's no life on Mars. What I'm saying is that you would land where in the zone of Mars, surface, equatorial latitude, where the humans would go, and you would confirm to some reasonable level, due diligence is what it's called legally, that there's no life in that material, so that the astronauts would not be, the dust that the astronauts would be tracking on their spacesuits would have been shown not to contain any evidence of life at some reasonable standard. You are correct in that this does not prove that there's no life anywhere on Mars. And that leads to the second issue of the second Genesis. You may decide that there's no life on Mars for the purposes of astronauts landing in the equatorial regions and coming back to Earth, and you may satisfy that requirement from terms of safety of the astronauts and the Earth's biosphere. And yet, when a human base is there, an extensive exploration, they may still discover life. Right? As you say, it is very hard to prove a negative, but you can prove it locally. And I think you're going to want to do that for a lot of reasons, some of which have to do with just science planning and bringing the astronauts back and avoiding the kind of debacle that they had with Apollo and quarantine the astronauts when they come back and all the costs associated with that. I think you'll want to have removed that issue completely from the discussion and the mission planning, and you can do it in advance with robotic missions. So you're in a position to be able to say, hey, I know that the area that they're landing on is good enough in terms of absence of life that these astronauts don't need to filter the dust to extreme levels to prevent contamination. They don't need to worry about getting sick. They don't need to worry about bringing dust home. We can relax all these constraints that might get imposed, and it can be done with a mission advance. You're right, it is not in the same category as these other constraints, but I didn't claim that it was. I'm just saying these are fundamental questions that we have to address. And if we don't address them, we risk derailing the story of Mars exploration that we would like to see implemented. By certainly, in no means are these the same. You can't say that adaptation to 1/3 gravity is the same category as volatiles on Mars or life in a second Genesis. I didn't mean to imply that. These are four fundamental problems, fundamental questions, the answers of which we will only find on Mars. That's my point. No amount of engineering on Earth will give us the answers to those questions. We got to go to Mars to get the answers.
Okay, I'll let other people ask questions.
Next question. What is the status of the 1996 Mars rock?
The rock in 1996 a meteorite called ALH 84001 was suggested to contain evidence of life on Mars. Since then, that meteorite has been the source of much investigation and much discussion. The conclusion is that it does not contain evidence of life on Mars. It does contain evidence of an early period in Mars history when it was more habitable, more Earth-like. So it's an interesting meteorite. Mars, it points us to an interesting phase of Mars's early history, but it doesn't really answer the question of life.
Last question. Can you comment on the long-term effects of the Martian environment, specifically the fact that the Martian day is 39 minutes longer and 1/3 the lower gravity? What effects will this have on humans long-term?
Yeah. Well, the 39 extra minutes, I don't think will be a big deal. I could use them today, actually, extra 39 minutes. I don't think that's a major issue. The 1/3 gravity, we have no idea. Not just me, but none of us have any idea what the effect of 1/3 gravity will be. We assume that we'll adapt fine and we'll just be just like living in 1 gravity. And maybe that'll be the case. The one sign of hope is that plants grown in space station at 1/3 gravity seem to have much better response to gravity than they do when they're grown at microgravity. So just looking at very limited data from the space station and only at plants, one would argue that the threshold for gravity response occurs above 0, but below 1/3, and that 1/3 and 1 is about the same for plants. Now, whether it'll be the same for humans or not, we don't know, but we are hoping it will be, and we are assuming it will be, but the only way we'll find out is by going there.
Thank you very much, Dr. McKay. Thank you for being with us. And good to know there's still lots of questions to know about Mars before humans get there, but that's the reason why we want to go to Mars, is to find out the answers to all these questions. On to our next speaker. It gives me great pleasure to introduce another exemplary and hardworking senior planetary scientist at NASA Ames, Dr. Carol Stoker. She specializes in Mars exploration science and technology and is actively involved in the robotic exploration of Mars and in planning for future human exploration. She often works in extreme environments on Earth to advance understanding and improve the approach to explore Mars. Please welcome Dr. Stoker.
Hi there. Just like everyone else, I'm wondering if you can hear me.
We can hear you.
Does it sound okay? Hi, everybody. I'm living in the third world country that is Northern California. And when the wind blows and the power company is afraid of starting fires, they just shut your power off. So I'm kind of here in a limited mode. The only internet that I have is coming off my cell phone. So I'm going to have James display my slides for me, and he's got first slide up. So this is actually a very good follow-on to the talk that Chris just gave, because I'm going to talk to you about what is the latest thinking about the most likely habitats for extant life on Mars. So if we're going to look, where do we look? Okay, so let's go to the next slide. So as Chris mentioned, the Viking mission, which was actually the first landers ever to land on Mars in 1976, was the only mission to ever search for extant life. There were 2 identical landers because they actually had low confidence that they would both succeed. So they made 2 of them as a way of improving the odds that they'd actually get anything. One was sent to the mid latitudes, the other to a high latitude site, and they both were identical. So they contained 3 life detection instruments that searched for evidence of metabolism. The only other instrument that they had on board, other than a very crude camera, was an organic analysis instrument which is called the gas chromatograph mass spectrometer. And that instrument was simply to look for the presence of organic compounds. Let's have the next slide. Next slide, please. Okay. So the Viking, oh, got to go back one. Okay, the Viking biology experiments basically were based on the best knowledge of biology that we had in about 1968 when these instruments were chosen. That is a very limited understanding of biology compared to today. But anyway, they were invented from first principles. So these instruments did an attempt to culture microbes from soil. And they attempted to do this by pouring a nutrient medium into the soil. And then the nutrient medium in many of the cases was actually labeled with radioactive carbon so that they could look at what was given off. So they were looking at respiration. They were looking at what happened when you added this nutrient medium. Did you get growth? And what happened was that as soon as the nutrient medium was added, the soil essentially immediately reacted. Now, typically with biology, there's a lag time, but in this case, the reaction was immediate. And the reactions were somewhat like they had predicted if you had life, but they were different in detail. And again, there were 3 of these instruments. All 3 of them were supposed to get corroborative results, but only one of them gave results that were fully consistent with biology. And that was the label release experiment that Chris mentioned, the PI of, to this day believes he found life on Mars. But the clincher was the gas chromatograph mass spec, which was there only to detect organics. It really wasn't a life detection experiment, but it showed no organics in the soil at all. And that was thought to rule out biology. Well, it turns out that was a false negative. And we didn't find that out for many, many years. But most recently, the Mars Science Laboratory has proved that there are organics present in the soil, but Viking simply missed them. Next slide. So the Phoenix mission landed on Mars in 2008 at 68 degrees north on ice-rich terrain. The objective of that mission was to search for a habitable environment, to search for organic carbon, and to measure the chemistry of the soil. It turned out that the organic carbon instrument had problems, again, similar problems to the problems that the Viking organic carbon instrument had. But the chemistry instrument, the PI of which is actually giving the next talk, discovered 1% of the Mars soil is this very weird element, compound, salt. It's really a salt, perchlorate. It's a form of chlorine with a lot of oxygens attached. So why is perchlorate important? Well, first of all, it burns organic carbon. It likely burned the organic carbon from the soil that was put into the Viking GCMS, turning it into carbon dioxide. And in fact, the Viking instrument measured carbon dioxide when the soil was heated up in the GCMS. The other interesting things about it is that it's food. There are many microbes that can use it for metabolism. In fact, they do something very similar to oxygenic metabolism. So it's a very high energy source of food. It's also antifreeze. It can lower the freezing point of water to almost minus 70 degrees centigrade, which is a typical temperature found in the polar regions today. Next slide. So things had pretty much after Viking sat for almost 40 years with a conviction that there was no life on Mars, and Viking had proved it. And Dr. Zubrin's point that you can never prove a negative was sort of refuted by Viking, because Viking got this one result. It was a very ambiguous result, but it was interpreted as a negative result. And then all of the subsequent missions never looked for life again. Well, just recently, there was a workshop called Mars Extant Life, What's Next? And at that workshop, there were 4 types of potentially habitable environments that were discussed as warning the search for life on Mars. That paper from that workshop has been published in Astrobiology, and I'm going to go through those potential habitats next. So they are surface salts deposits, ground ice, caves, and deep subsurface liquid. And I'll go through them one at a time. So next slide. So salts. It turns out that the salts, chloride salt deposits have been mapped on Mars, and there are at least 640 sites identified that appear to be either small lakes or some kind of a groundwater influx to the surface. And members of the group that I work with, and a former postdoc, now AIM scientist, Alfonso de Villa, has been studying salts in the Atacama Desert, which are, the Atacama Desert is the driest and most hostile place on Earth that isn't a polar region. And there are microbes, endolithic cyanobacteria, that obtain water from atmospheric humidity via a process called deliquescence. And they basically live under the surface of these salts, which are effectively dry ponds in the Atacama. It is also known from a lot of research that viable microbial colonies can survive for up to hundreds of millions of years inside salt crystals in fluids that are trapped in the salt crystals. So salts are a location where evidence of life and possibly even living organisms might be encountered on Mars today. Next slide. Okay, so it turns out that evaporite minerals, which include salts, I mean, salts are evaporite minerals, are likely things for the Perseverance rover to encounter at Jezero Crater, because basically it's going into a dry lake bed. And if found, these would be important samples to return to Earth. So let's go to the next slide. And by the way, it lands on February 21st of 2021. And finally, this horrible year, 2020, will be over. So, okay. The next candidate site I'm going to talk about is ground ice. This is showing you a map, also recently published from Pico. I hope I'm pronouncing that correctly. And it is a global map showing the location and depth to ground ice across Mars. Now, ignore the big black blob in the middle. That is actually an area where their method didn't work. So the colors show you the depth to ground ice. And what you can see is that all latitudes above 40 degrees north have ground ice within a meter of the surface, according to this map. And in some areas, like on the far left, near about 40 degrees north, it's quite close to the surface, like 20 centimeters. So the white squares shown here are locations where fresh craters have revealed white ice. So basically this is from the high-rise imaging. And they have time-lapse, essentially time-lapse imaging of the same site, and then suddenly a white spot appears. And that's where a crater has recently impacted and exposed the ground ice. And measurements on those craters have shown that this ground ice is within 50 centimeters of the surface. So these are low latitude and sites where there is clearly ground ice near the surface. Can I have the next slide? So this plot shows a climate model. So now a fairly old climate model. It's published in 2005 by Richardson and Mishna. And it shows where pure liquid water is thermodynamically possible on the current surface of Mars. And what you can see, and by thermodynamically possible, what I mean is that the pressure and temperature conditions at the surface are met. And this is a map of how many days a year, that's what the color coding means, how many days a year those pressure and temperature conditions are met where pure liquid water could form if there were a source of water. So for example, if there were ice at the surface, that ice potentially could melt. It doesn't mean the water is stable. It doesn't mean it will sit there forever. It will evaporate, but it can form. So basically, this is where it occurs today. Let's go to the next slide. So what it's telling you is that these near surface ground ice deposits could be quite warm if they're at 40 degrees latitude, more or less. Now, what happens on Mars is that the tilt of the axis changes really quite radically over time. And currently, the tilt of the axis is about 25 degrees. But 5 million years ago, the tilt of the axis was about 45 degrees. And the average tilt of the axis of Mars over time is 35 degrees. So as the tilt of the axis changes, the amount of sunlight that falls on high latitude locations also changes, and it increases. So what you can see in the bottom plot is this kind of up and down tilt of the axis. That's what's being displayed, is the tilt of the axis and how rapidly it occurs. So in a million years, you get about 5 or 6 up and down cycles of the tilt of the axis going from essentially 0 to 45 degrees or 30 plus degrees. And then as you get back 5 million years ago, the average goes up to like 35 degrees, and it's going up and down up to 45. And so basically, during those conditions, the high latitude ice on Mars should get a lot warmer. So let's go to the next slide. So this is that same climate model, which is run for the condition of the tilt of the axis being 45 degrees. And this is showing you, again, the number of days a year that the pressure and temperature conditions would allow pure liquid water to form. And now you see that for something like 50 to 100 days a year, up around 60 to 68 degrees, which is where Phoenix landed, you can have pure liquid water form at the surface. So other modeling has shown that when that occurs, when you have 45 degrees obliquity or 35 degrees obliquity, you can get a significant amount of melting of the ground ice, which Phoenix found to be at an average depth of about 4 or 5 centimeters. This is just a couple of inches below the surface. So what you can have now is the ground ice melts all the way down to a meter depth, or at least it's warm enough to support metabolic activity of terrestrial-like microbes, all the way down to almost a meter depth when the obliquity is up to 45 degrees. So this logic led to a mission, which is in the next slide, or at least it led to a mission proposal. This is the Icebreaker mission, which is proposed to Discovery. We last proposed it in 2019. Chris McKay is actually the PI. It's a Lockheed Martin spacecraft, which is the same lander as Phoenix and InSight. It carries a 1-meter drill and 2 life detection instruments, plus a later generation of the chemical analysis instrument that was flown on Phoenix. So that is a planned, maybe not selected, but a planned life detection mission to go look at, is there life in the ground ice? Okay, so let's move on to the next type of environment, which is, next slide, caves. So here again, on the left side is a map showing the location of a number of potential lava tube caves on Mars. So basically, in the imaging of Mars, you can find places where there appears to be a hole in the ground. As a matter of fact, there have been over 1,000 of these that have been mapped. And some of them are shown in the map on the left. So caves are an attractive and interesting target for biology, potentially, because they could be warmer and wetter than the surface. They are sheltered from ultraviolet and cosmic radiation. And so they are potentially a environment for life on Mars that has a growing advocacy community, I should say. The cavers, the Earth cavers, are really excited about this. Okay, next slide. Microbes in caves are not like normal microbes. They tend to, one of my caver friends, Diana Northrup, calls them microbes masquerading as minerals. So they tend to look like rocks. They have to be collected and looked at. If you're going to look at what they look like, you have to look at them with a scanning electron micrograph. And so if you see the blue thing on the upper left, that is a it's a water drop with a forming off of a very tiny stalactite that is blue colored. And a sample out of that, looked at with a scanning electron micrograph at like a 1 micron resolution, shows these really very unusual patterns that almost look like the skeletons of cactuses. And that is one of the things with the microbes in caves. They have extremely unusual morphologies that are not really found in other microbial environments. Another example is at the bottom left, this yellow looking mineral. This is found in lava tube caves in Northern California called lava beds. And it's spectacular. It's gold. It looks like there's gold all around you, and it's sparkly. I really recommend anybody that's interested to go there. Again, images with a scanning electron micrograph, you can see these microbes. And these are actually more or less normal looking microbes in this particular example. But caves they're pretty difficult places to even get people into. It takes you have to take a lot of power with you in terms of batteries, and it is not the easiest place to explore. But the Perseverance rover is carrying a drone. I'm sure that's going to be talked about here. To me, it's maybe the most exciting thing about the mission. The drones could be a very important technology to evaluate the habitability of caves. But we're going to need technology advances to accomplish sampling. And it would be actually useful to have humans involved in that. Okay, next slide. Okay, so the final environment that is of interest to as a habitable environment on Mars is the deep subsurface. And basically there has been a lot of buzz about a deep lake on Mars. You've probably seen something about this if you've been watching the news. There's an instrument on ExoMars. This is a European mission. It's actually been flying around Mars for more than 10 years. And it has an instrument called Marsa's. It's a radar sounder. And the Marsa's data has been collected over this 10-year period, has been reanalyzed with some new methods to explore the potential for subsurface water and pick signal out of noisy data by averaging lots and lots and lots of overflights with this instrument. And they have recently published in Nature evidence of a subsurface lake beneath the south polar layer deposits on Mars. And the lower image is actually their map of these lakes. And again, this is a paper by Lauro et al. It's an Italian group, and it's in Nature Astronomy. I think it's a month ago. So what they're showing in this map is that there are dielectric permittivity, that's basically what the radar returns, values, and if they are larger than 15, that suggests that it's liquid water, that is, that the radar is being reflected off a high conductivity surface, is the way of thinking about it. Largest dimension of the biggest spot there is 30 kilometers. It's a mile, it's a 1.5 kilometers beneath the south polar layer deposit. And in order to get to that, you would need advanced deep drilling to access this type of environment. Let's go to the next slide. Well, luckily enough, automated wireline drilling is coming along. And in fact, our friends at Honeybee Robotics recently demonstrated in Greenland drilling to 110 meters with a wireline drill in a recent field campaign. And the picture on the right is sort of an illustration of how this drill works, but it's basically on a cable, and it inchworms its way under the ground. This is the only way you're going to be able to get enough drilling equipment to drill a kilometer-ish on Mars. It's probably a stretch to imagine that you can do this robotically. I think it's a very attractive kind of target for human exploration. Okay, last slide, I believe, is my conclusions. So if Carl Sagan were alive today, I'm sure he would say, it's been 43 years since Viking. Isn't it time we resume the search for extant life on Mars? I have discussed 4 potentially habitable places to search for life. Salts and ice can be sampled with current robotic technology, if we just had the will to do it. Caves in the deep subsurface aquifers will require technological advances for access and sampling, and are attractive targets for human exploration. And that's the end. I think I have a couple of minutes for questions.
Yes, you do. Jay Kuznets is going to ask a question. Go ahead, Jay.
Okay. If the Mars Lab rovers scoop up Martian microbes for real, can they give definitive clues apart from sophisticated organic compounds?
Well, so the answer is it totally depends on what type of instruments you fly. So because of the long, I would say, arguments about whether or not the Viking biology experiments were detected life or detected weird soil chemistry, we have our group has adopted the philosophy that we should really look for biomolecule compounds and not do metabolism experiments. But that's just a point of view. understanding the chemical environment at which is on Mars, which was not really, we had no understanding of Mars when we flew Viking. I mean, really, and we had very limited understanding of biology. So, we have a lot more sophisticated approaches available today. But I think it's one of the problems has been that because since Viking, there has been this really strong bias that said there's no life on Mars. There's no point of looking for it. There has been no money, virtually no money going into instrument development to search for life until basically the last few years. And even in the last few years, it's been targeted at Europa and Enceladus. It has really not been targeted at a Mars-like environment.